So COVID-19. COVID-19 is a pretty horrific illness and there's a lot of misinformation that's out there about the illness. So what I'm going to do, I'm going to go over it today and explain to you COVID-19, why it's such an important thing to stay in the house, why it's such a tragic illness, and why it's not flu. And we'll go through some of the ways that it's treated and why it's so bad. So let's start first things first then. So what is a virus? That's probably the biggest thing that we'll want to get out of the way straight away. So a virus, most people think viruses are living. A virus is not living in any way, shape or form. All a virus is, if we look at this virus here, there's three main parts that you need to concern yourself with, especially when it comes to COVID-19. So you've got the main membrane, the green part here. That is basically made of fat or lipids. You've got the bit in the middle here, this squiggly line. This is the RNA or the genetic code. So this is the genes that get passed on to reproduce. And then you've got these spikes on the outside, and these are made of protein. And these are receptors that they use to cling on to other cells. Very similar way. So what a virus does, it basically comes along, and remember I mentioned about these spikes. What happens with these spikes, each individual cell in your body has receptors for other things to sort of latch on. Think of this like a spaceship where it's got the docking station. So that's the same thing, it docks, but some docking stations won't fit all spaceships, and it's the same with viruses and with your body cells. Some of them are different shapes and they respond to different things. So a coronavirus is very clever in that it's the respiratory cells, so basically from your nose all the way down into your lungs. There's receptors there, it comes along, it's the right shape. Your body cell recognises it as being friendly, even though it's a virus. Virus comes along, latches on, and then one or two things happen. Either the virus will sort of stay in the wall of the cell that you can see here, or what it will do is it will actually get inside the cell. Either way, in every occasion, what it does, this little squiggly genetic code here, it puts this into the cell, it goes into the nucleus of the cell, and what that does then, that becomes a factory for additional genetic code for the virus and for the components that make up the virus itself. So this cell now becomes a slave to the virus, and it produces a lot more of them. As you can see here, tons of them. And then once it gets to a certain point, one or two things happen. The cell itself either ruptures and all these viruses come out, or what you'll have is they'll all basically, they sort of find a hole in the side of the cell wall and sort of open up a gap, slip out, and then the gap slides behind them. Now, the reason that this is important, or more specifically why this relates to humans, is the symptoms that you end up getting. And we've looked at COVID-19 specifically. There's four main symptoms that people are sort of coming up with at the minute. First one that most people know is a cough. There's a big cough, and all that is all these cells that are in your respiratory tract have been irritated by this virus. If you think of all this extra stuff that's going on in the cells, they swell, they get inflamed, your body realizes this is not a good thing, so you cough to try and get rid of whatever's irritating all these cells. The next one, and this is one that's just came to light in the last sort of few weeks, is a lot of people have said that their sense of taste and the sense of smell is disappearing when they end up with being infected. This is one of the first symptoms before anything else happens. Again, this is the same thing. The cells in your nose, the cells in your tongue, they get inflamed, they get irritated by the virus, and they don't function the same way, so that's why you lose the smell and the taste. And another one is bloodshot eyes. Again, the same thing. These viruses get into your body and they're introduced via the mucous membrane. So anything that basically is damp, your eyes, your nose, your mouth, that's where the virus gets exposed to, and that's where it takes hold, and then it travels through and it starts infecting the rest of the body. That's why it's really important that we don't touch your face, we don't touch other things and then touch anywhere on our face or our eyes. And that's why doctors, nurses have the face shields and the mask, and some of them with goggles as well, so it doesn't get introduced to the body. So that's viruses, and that's how they work. So now we've got that out of the way, let's look at COVID-19 specifically, and we'll look at some stats and facts and figures. So I'm going to grab my pen and let's have a look. Let's do blue. And what we're going to look at is we're going to look at some of the stats here for other illnesses. Now this is important to try and understand why COVID-19, why it is the way it is, and why it's so important that we stay in this lockdown. So for those of you who don't know, COVID-19 is actually a derivative of SARS. which was big in about 2003. This was one of the pandemics that they thought was going to take hold. As it happened, it didn't, not in the same way that they thought it would. But that was SARS-1. So SARS-CoV-2, COVID-19. It's the same thing. So it's a derivative of SARS, which was severe acute respiratory syndrome. So it's all respiratory. You had MERS, which is Middle East respiratory syndrome, very similar, but that only affected basically the Middle East. And if I put in fatality rates here, this will hopefully give you some context as to why things are the way they are. So SARS had a fatality rate of roughly 15%, which is not good. There's quite a lot of people. MERS, on the other hand, had a fatality rate of 34%. Now, most people haven't heard of MERS, and I'll get to that in a second as to why, and why this wasn't as bad as it could have been. If you look at H1N1, which was swine flu, which is the one that a lot of people in the world were infected in, if you look at the fatality rate, it's really low, 0.02%. So very few people. That's actually less than the flu, which is the next one, which is seasonal flu, is about 0.1%. So that's about 1 in 1,000 people with that one would end up dying. Interestingly, H1N1 sounds really technical, sounds something newfangled. Seasonal flu is actually H3N3. So there you go. It's just another name for it. We'll look at COVID-19. Now we'll get to that in a second because I'm going to explain this further, and then we'll get to where it is. If we look at Ebola. Now Ebola was really nasty. So I had a death rate, fatality rate of somewhere between 50 to 70%, and that basically depended where you were in the world and the kind of treatment that you were getting. So even if you go 50%, 1 in 2 people that get Ebola will die, which is pretty horrific. And COVID-19, depending on where you are in the world, and because this is ramping up so quickly, it very much depends on the death rate. So the USA, if I can just squeeze these both in, USA is about 4%, and the UK, if I just put this to the side here, as of today, which I think is about the 13th of April, is sitting about 12%, which is not good. And obviously Italy, Spain, France, they've all got pretty high death rates. And I'll explain that in a second when we go through this as to why that's the way it is. So each of these viruses have got their own pathway. Now I mentioned about the virus, how it works, why it works, but let's look at a bit of the evolution and where these viruses came from. So if we look at, so let's look at MERS first. So this is MERS here. MERS developed from a bat. It passed across to another animal. It started infecting camels, of all things. Infected a camel, and then it infected humans. Really bizarre. Very different virus. Because of the mutation, and I'll touch on mutations later on, it became a lot more deadly when it ended up infecting humans. If you skip down to this one here, it's a cat, so a cervet, which is a kind of cat. This is SARS, so it went from a bat to a cat to a human. Bats, by the way, have a lot of coronaviruses, like lots and lots of them. So that's why bats seem to be implicated in a lot of these. And if we then look at COVID-19, it was a bat. It went to a pangolin, which is kind of like an armadillo type animal. Infected the pangolin, but then infected humans. It made that jump across species again. And if you look at H1N1, this is a really weird one. It came from pigs, it infected birds, and then it jumped across to humans. So the evolution of them are quite different, but the main ones we want to focus on are MERS, SARS, and COVID-19 because they're very similar. So there's a few key things that you want to get your head around. In fact, I'll come over this side so it's probably easier. All these illnesses have got a very different infection rate. So if you look at something like measles, when that takes hold, it really takes hold. It's really infectious and it spreads really far and wide very quickly. So what we use to term this is what's called r-nought, or reproduction or replication rate. So r-nought is a figure that you might have heard, and this is important. Once you understand r-nought, it helps you understand the evolution of a virus going forward and how it's likely to affect. So r-nought is very simply given as a number. So if we look at some of the r-nought figures for these illnesses before, so SARS r-nought was 2. So that means if one person gets infected, they will roughly infect 2 people. MERS was 0.7. Now this was critical for MERS for it not taking hold. Remember, the death rate for MERS was 34%, which is really high. But that meant that it could infect less people because it was 0.7. H1N1 is it's about 1.8. Now these figures are not an exact science because it changes, but it gives you a rough feel for it. Flu is 1.3, and I want you to keep a note of the flu one there, and I'll explain why this is important in a minute. Ebola was 2. So a lot of people were panicking about Ebola, thinking it was going to really take hold and it was going to infect the whole world and everyone was going to die from it. But actually, it's quite difficult to get infected with Ebola, relatively speaking, when you look at something like measles. So it wasn't easy to actually contract Ebola. If you got Ebola, then yeah, that's bad because you're not going to live too long. COVID-19, interestingly, is sitting roughly, and this is not exactly at the minute, it's not been nailed down because there's so many variations. For example, if you look at Italy versus Singapore, USA versus something like the Solomon Islands, it's all very different. But roughly it's about 2.6. So for every one person that gets infected, they will infect about 2.6 people. So if you look at this, so the rates here, so your R0, your infection rate. The higher your infection rate, that's bad. Because it means you can infect a lot of people. If that was at 100, that would be horrendous. And what we see with COVID-19 now, if that was an r-nought number of 100, the whole country would be infected by now. A lower rate, that is definitely good. So the lower that r-nought number, the better. Now, I don't know if anyone, maybe I'm showing my age here, that can remember the song 3, it's a magic number. Well, in this case, 3 is not the magic number. The magic number is actually 1. So if you've got an r-nought of 1, that's where things change significantly. And I'll go over and explain this now. If r-nought is 1, what that means is you'll infect one other person. So it makes it very difficult, if anything is below 1, for a virus to spread because it's not infecting more people than are already infected, if that makes sense. So if r-nought is 0.5, it means for every one person that gets the virus, they'll infect half a person. So it's getting half as many people infected every time, if that makes sense. If you get something that's 2, it means it's doubling every infection cycle, which is bad. If you had something like measles, which from memory I think is anywhere from about 8 up to 20, and I've heard some numbers really high depending on the environment of up to 100, that is really bad because you're going to infect a lot of people very quickly. So when we look at this r-nought, so that there's a few things that we need to just get our head around and make sure that you understand this. And this is why it's really important to understand COVID-19 and the r-nought figure and why this makes it so potent. So we've got that dash line there. That is your r-nought figure of 1. Below the line, good. Above the line, bad. So if we look at something like MERS, what that basically does is it does this over time. And it fizzles out. It stops because one person gets infected, they only infect 0.7 other people. So it's not going to work in the same way. If 10 people have it, that means in the next cycle of infections, there will only be 7 people that have it, and so on. It will keep reducing. So that's what will happen there. If we have something like, what do we say, Ebola. Ebola is about a 2% infection rate. So that's bad. So what ends up happening, you get one person, and very quickly it does this. And it goes up. Sorry, that was COVID-19. Ebola, which was 2, it'll kind of run along. So let me just get this, scrub that one out. Ebola will run along very similar, but it's not going to be quite as virulent. It will sort of go like this. And then you've got something like seasonal flu, which is 1.3. So it actually makes it quite difficult to get infected with the flu. So if it comes along the 0 line, it kind of sort of does this. It doesn't climb very quickly. It does climb, but not in the same way. If you notice the difference between these lines here, there's not a big difference between them. So it's 1.3 for this line and 2.6 for this one. So it's only double, which doesn't sound a lot, but actually doubling makes a huge difference. And this is the big thing that we need to get our head around, is the doubling rate of a virus. So I've got a young son, and when he started school, one of the things that he really enjoyed was math. So I said to him one day, I set him a problem and I said, would you rather I give you $10 or would you rather come back in a month? And what I'll do is in that month, every day we'll start off with 1 penny and I'll double it. So the next day you'd have 2. Then the next day after that, you'd have 4. And I'll keep doing that for a month. What would you prefer now? Would you prefer $10 now? Or would you prefer that double the money in 30 days I'll give you how much money? And he straight away said $10. Now actually it's an interesting one, and this is why viruses are so bad when they get started. If we did this with a penny on day 1 and we doubled it for 10 days. If I said to you now, would you take $10 now? Or would you want the money that we get to in 10 days by doubling? What would you take? Now have a think about that. What would your answer be? So I'm going to tell you what the answer would be, and I've scribbled these down here just so I don't get them wrong. So in 10 days, your $10 would be worth $10.24. So if you took the $10 now versus in 10 days what you would have had, you're pretty much breaking even. Doesn't make a big difference. This is where pandemics get their power. So in 30 days, would you rather take $100 now or take the money that you'll get on 30 days from now? So have a think about that. What would you do? Would you take $100 now or take the money that you would have in 30 days time? So I'm going to give you the answer again. I've scribbled this down. I'll get my piece of paper because I've never remembering these numbers. So you would have $5,368,709 after 30 days just by doubling every single day. If you leave this for 90 days, would you rather have $1 billion today, or do you want to wait for the 90 days? I think you're getting the theme of this now. You definitely want to wait the 90 days because it's such a big number. 6.19 times 10 to the 24. So for those of you that can't remember back to high school, what that means is 6, 1, 9 and 22 zeros. It's actually a number called a septillion. It's huge. That is exactly what happens with a virus and pandemics. It's like you're doubling the penny every infection cycle. So infection cycle's a real big one to get your head around, and this is where the power comes in of COVID-19, and this is why all the numbers are increasing so quickly, even although most countries are on a lockdown. So if we go back to something like the MERS, which is 0.7, a lot of people died with this, but actually it didn't really take hold. And the reason being is because this r-nought number was below 0.7, but there's another part to this equation, and this is called the series interval. And what the series interval is to explain it, is basically the time it takes from one person to get infected and then another. Now there's two sides to this, and this is the other side of the coin and why it's really important. So if we look at the series interval, so if you look down here, and hopefully you can still just about see me there. So if we've got patient 1 here, they get infected here on day 1. They start showing symptoms about day 4. For COVID-19, it's about 3-4 days. And then they're infectious for about another, let's say 10 days, so day 14. They infect someone else, let's say whoever they live with. So let's say it's a husband that infects the wife. This time here from day 1, from them being infected to them getting symptoms, this time in here, that is what is known as your series interval. The series interval is the time that it takes from one person to infect another person. And this, coupled with your r-nought number, is what causes pandemics to either take hold, such as COVID-19, or die off, such as MERS. And this just keeps repeating itself. So there'd be a 4-day series interval. There'd be 4 days there. So when we start looking at this and we look at the combination of the series intervals, now some people with COVID, it's actually taken 8 days. So if we did that, that's good. So very long story short, a short series interval, so a short time between infecting another person, bad, very bad. So if it's a day between, that is horrendous. And the reason being is, if you think about it, If someone gets infected with an illness, they infect someone else within a day. They then infect another person. So within 7 days, one person has infected 7 people. But person number 2 has also infected 6 people in those 7 days. You keep doing this, it stacks up really quickly. So a short series interval, so a short time between infecting people, that is bad, real bad. A long series interval between infecting people, that's a good thing. Very good. And this is what saves nasty illnesses from being nasty for an individual to being pandemics. So again, if we start looking up here and we fill in some of the figures for the series interval. So if we look at SARS, the series interval for SARS was about 7 days, which is not too bad, not too shabby. You look at something like MERS, it was 14.6, so we'll call it 15 to keep it easy for the figures. H1N1 was about 3 days. We look at seasonal flu, that's about 3 to 4 days, depending exactly which strain it is that's circulating. Now remember Ebola. Ebola is actually r-nought, 2 people, so it's going to increase. That will create an epidemic, and it's got a 50 to 70% death rate, but Ebola's series interval, so the time between infecting others, is 14 to 28 days. So that means one person gets infected, they fall ill, they get the symptoms, they then go to the doctor. It's taken them about 14 to 28 days to infect someone else. So although it's quite transmissible, it's not, it doesn't have a short series interval, so it's difficult for it to infect another person time-wise. So that is why Ebola is very unlikely to become a pandemic worldwide. And if we look at COVID-19, so COVID-19 depending, and again this is all kind of up in the air at the minute, is somewhere between 4 to 8 days. So if we go for the middle, it's 6 days. So again, we go up and look at something like SARS. So it's got a series interval of 7 and an r-nought of 2. COVID-19 is 2.6 for its r-nought, but it's 4 to 8 days before it, for the series interval. So SARS is not quite as bad. MERS, even less so. So this is why when you've got those two things, your r-nought plus your series interval, that makes things good. So if you come down here and look at flu, so the r-nought figure is actually quite low, but the series interval of about 3 to 4 days is relatively high. So seasonal flu overall actually infects quite a lot of people because of that. If we get Ebola, I've already mentioned this, the r-nought, relatively high, not sky high, but the series interval is days, it's weeks and weeks between them, which is good. COVID, the r-nought is about 2.6, but the series interval is about 4 to 8 days, so if we call it 6 in the middle, oh, it's arrows, that's what I meant to do it. Relatively high transmission rate, but the series interval, 4 to 8 days, is kind of somewhere in the middle from these other illnesses. So that's why COVID kind of takes effect and it ramps up really quite quickly. So just to let you understand as to why social distancing and why this is such a big thing and why we want to do it, and more importantly, why we want to stay at home and stay out of the way. If we look here, if you've got your one person that's been infected, for ease here, I'm going to say that COVID-19 has an r-nought figure of 2, so one person will infect 2 people. So every 4 to 8 days, we'll go for the middle, for the series interval. After roughly 6 days, 2 people will have it. After 12 days, you'll have 4 people with it. If you go to 18 days, you're going to have 8 people. 24 days, you're going to have 16. 30 days, you're going to have 32. And so on, and so on, and so on. You can see these numbers very quickly start building up. To the point, you keep going with this, after about 90 days, and I can't remember the exact figures, but it's somewhere in the region of about 4 to 5 million people infected, which for roughly in the USA, 75% of people, 80% of people will have mild symptoms similar to the flu. 20% of people will need to go to hospital. So when you've got 5 million people, that's 1 million people that require hospitalisation within a 90-day period, and that's over and above every other illness, every other issue that people go to hospital for. So that's an extra 1 million people that go into hospital. Roughly 5% of people that are infected with COVID-19 will need intensive care. That means they will take up an intensive care bed. If we're working on 5%, that'll be 250,000 people within a 90-day period, in addition to what the hospitals are already dealing with now, will need intensive care. That is the crux of why COVID-19 is so bad. It's the amount of people that will need hospitalisation with it. And just to give you an idea, a lot of people, I've seen a lot on social media, I've seen a lot of people having the conversation saying, well, I'm only one person, doesn't matter, I'm not infected. 30% of people with COVID-19 have no symptoms. So by all rights, I could have COVID-19 right now. I could decide that I'm going to go out to the supermarket, don't wear a mask, cough once or twice, or rub my face, pick up a tin of beans or something, pint of milk, and then put it down. Someone else comes along, picks that up, they're now infected. One person, what difference is that going to make? There's a real interesting case study in South Korea. South Korea were doing fantastically well. When it first landed in South Korea, very quickly they had it down to about 30 cases, and it never really went anywhere from there. Until patient 31 came along. Now patient 31 was a female who didn't realise that she was infected with COVID-19. She was feeling a little bit unwell and decided to go to the hospital. When she went to the hospital, she couldn't get tested. When she was at the hospital, she went to church because she was religious. The church that she went to is what's known as a mega church, so there was a lot of people at this church. This one patient, when they started doing all the tracing and contacted all the people that were at the church on that day, she had managed to infect 5,016 people. One person, 5,016 people infected without even realising it, because she was in such a close confine area. It was within a church, all people crammed down. She's walking past a lot of people, and she infected all these people, who then went out, obviously infected a lot of other people, and it kind of took hold. Thankfully, South Korea had a real strong contact tracing program. So people that were in this church, they contacted them all, they traced them down, and they got them to self-isolate. And if you look at South Korea's numbers now, from memory, I think they're sitting around about 10,000, of which 5,000 were from one single patient. So 50% of their cases were from patient 31. So it's a real interesting study, that one, and it's worth having a look on Google and seeing what you can find there. So what I'm going to do, I'm just going to move my camera. We're going to then go on, and I'm going to show you exactly why COVID-19 attacks the body, what it does, and why it's so dangerous for you as an individual. Right, so we're back. Let's go over this. And one thing I want to address, a lot of people have said that this has come from a lab in China, and there's a bioweapon, all the rest of it. I want to just very quickly touch on this, just to help people understand viruses and why scientists can say with pretty much certainty that this never came from a lab. So what I want to do is I want to go cast your mind all the way back to 1918. 1918 is when Spanish flu had happened. That was the first real big pandemic in the modern era that people can sort of remember. So Spanish flu in 1918, it was a virus, H1N1. Sound familiar? That basically came from a bird, infected a human. It was a novel coronavirus at its time. Again, it's a coronavirus. Humans hadn't been exposed to this before, so when this ended up in the wide open world, a lot of people infected, body couldn't deal with it, and they had effectively what's happening now with COVID-19. A lot of people died, respiratory illness, same thing. But this was back in 1918. So many people were infected by it. What ended up happening is people started building immunity to it. So when it came back, so when H1N1 is coming back now, it's people that haven't got immunity to it because they haven't got the antibodies. So what ended up happening? Asian influenza, which was 1957. Now if you look here, the RNA, so that's the genetic code, ribonucleic acid. It's in here. This is a genetic code and it's basically the instruction manual for this virus. As I mentioned before, it goes into your cells, it infects the cells with this genetic code, this instruction manual. Your cells then end up reproducing this exact same virus and churn more of it out, and that's why you get the illness. But what ends up happening, because of these viruses and the way that they reproduce, roughly 1 in every 10,000 of these, when they reproduce, will end up with some sort of mutation. It's how it happens. There are basically 4 parts of the code, and I won't complicate this. It's either T, A, G, C. All right? So these 4 parts, numerous combinations. So T could link up with A, then in the next one it could be T with G, or it could be A with G, or A with T. These all link up. Now you can imagine when these codes are quite long, you imagine going through and looking at a code, and you were doing this manually yourself, and then you had to write it down on a piece of paper next to it. If you had about 10,000 lines of this to do it, the chances are at some point you're going to make a mistake. And that's exactly what happened. Phone just went. Bizarre. So if you've got 10,000 lines of this code and you make a mistake, what ends up happening is you then put this instruction manual together. So think of this about building an engine. You've got an engine for a car. Let's say there's, 200 bolts, and you accidentally swap 2 of the bolts, and you put the engine together again, you start the car up. The car might run perfectly fine. It might be absolutely fine. You wouldn't even notice it. You could run that engine for the next 10 years, no issues whatsoever. But what could also happen is you start the engine up and it crashes, bangs, thumps, and it grinds to a halt. Horrible noise, smoke coming out of it, costs you thousands to get it fixed. This is exactly what happens with viruses. So this genetic code can get mixed up. And most of the time, nothing happens. It doesn't really have an effect. But what can also happen is the genetic code from another virus that's in your body. 2 of them can get into the cells at the same time. They can both spit their RNA into the cell. It starts reproducing this frantically. And what it can do is it can basically get virus 1, virus 2, and mix up some of this code and put it together and combine it. So think about this like baking a cake. Let's say it says to put caster sugar in, really fine sugar, and you put in brown sugar, and you grind up your recipe. It's going to taste pretty much the same. It's not going to be vastly different. But if it said to put in maybe sugar and you put in salt and you bake it, the cake might bake exactly the same. It look the same cake, but it tastes really different. Your body's going to have a very different reaction to that when it's salt versus sugar. So what ends up happening sometimes when these codes get mixed up, this is exactly what happened with Asian influenza in 1957. You had the H1N1, which now became the human virus, because that's the Spanish flu, and then mixed with H2N2, which is another avian virus, which was another bird. They basically went in a big mixing pot, big mixy blob, mixed up, and ended up with 5 strands of the genetic code from H1N1 and 3 strands from the H2N2 avian flu. So this was another mild, small pandemic that happened. Fast forward to 1968, we had what was called the Hong Kong influenza. The same thing happened. So the H2N2 human virus, which is this one, the new virus, it then combined with an H3 avian virus, another bird flu, and that became H3N2. And that's kind of how viruses evolve over time. So this is exactly what's happened with COVID-19. Now, I can't show you just now, but if you research, if you go onto Google and just type in COVID-19 virus mutations, you will see even in the 3 to 4 month period this virus has been around, there are literally hundreds of mutations. So if you think of each of these genetic codes with those 10,000 pieces of information in there, when one little bit changes, at some point in the world, scientists can track this and they can see where a specific strain came from, how it evolved and why it evolved and what happened with it. So when you have this is like a fingerprint. If you imagine there's 10,000 pieces of code, there's 4 different ways that this code can be interpreted. The permutations are literally almost endless. So for a lab to basically go in, work out which is the worst, which is the best, and produce a bioweapon, to do this, I think it's given viruses, it's basically selling them short. Mother Nature's way more devious than a lab could ever be. For a lab to basically go in and work out one or two permutations in billions and billions and billions of permutations to make it more deadly, it's difficult. It's just not easy to do in any way, shape or form. It's way more likely that Mother Nature has done this, and Mother Nature is way more devious than a lab could ever be. So that's how viruses evolved, and that's why it's very unlikely that this is a bioweapon. Very unlikely. So let's look now at what actually happens with COVID-19 and why it's deadly and how it affects the body and why people die from this. So if we look at a man or a woman here, you basically got the windpipe that goes down here, and then it goes off to both the lungs. Now the lungs, most people don't really understand how the lungs work. In real simple terms, the lungs are there for gas exchange. Most people think it's for taking oxygen. Actually, there's a two-way process to this. So I want to ask you a question here then. What is it that actually triggers you to breathe? What causes you to take that breath in? Or if you're holding your breath and for as long as you can, what causes you to eventually... Most people think it's because of lack of oxygen, and it's not actually. You've got plenty of oxygen. That's why CPR works when you do it to somebody else, because you've got plenty of oxygen in your breath still. It's actually a lack of it's an excess of carbon dioxide. When that builds up, your body really fights against it and makes you breathe, because when you breathe, you expunge, you breathe out carbon dioxide, and that allows the body to get rid of it. And that's really important, because carbon dioxide is slightly acidic. Your blood is in a very, very thin band of acidity or alkalinity, known as pH. If you deviate from that even very slightly, you become very sick, very ill. So your body does everything it can to keep that acidity in a very narrow band. So another thing that's really important to understand is posture really affects your breathing. And this is important when we come to understanding people that are on ventilators and why it's difficult for people to breathe, even on a ventilator. So if you're sick, I don't know if you suffer from asthma or you've ever had a really bad chest infection, most people struggle to sit up straight. And that's a bad thing. Most people sort of slouch and they fall down. Now, I was an EMT for 5 years, and one of the things when we ever went out to an emergency call for people, if they had asthma or they had a chest infection or things like lung cancer, they were always slouching and the breathing was really bad. What we would always do is sit them up. And the reason being, if you think about your lungs, what you basically have under your lungs here is your diaphragm. And what that does is, it's a membrane, and what it does is it basically the muscles pull it down, and when it does that, it basically pulls the lungs and it stretches them, and when it does that, it causes a vacuum in your lungs, and you have to go and breathe in. That's why when you breathe in, the bottom of your tummy actually, down here, kind of sticks out a little bit. That's really important. So when you are sitting up and your posture is good, gravity helps you, because it pulls it down. When you're lying down, you're fighting against it, and it's all your muscles, and it can become tiring. And this is really important when it comes to respiratory illness, and I'll explain why in a second. So your lungs, you breathe down in here, and your lungs basically branch off. They start big, small, and it goes really tiny to get to an alveoli here, which is it's a microscopic part of your lung. It basically goes down into a little sac at the end here. Now, ordinarily, I've put a thin blue line here, and hopefully you can see that really quite well. In here, there's mucus, there's moisture, and that helps with the gas exchange of the carbon dioxide to leave and oxygen to come in. If you end up with an infection in your chest, normally if that progresses to something like pneumonia, what ends up being produced in here is, to keep it very simple, effectively white blood cells will go to here, and they will fight whatever infection you have managed to introduce into your lungs. So let's say you've got a little virus has got in here, a little devious thing, and it's having a field all day. It's causing havoc in here. What happens is, then your body will send in something to fight it. So these are like the police, they'll come along, and what they basically do is they'll normally surround it, consume it. You'll cough, hence why with a chest infection you cough, because that action does this, it squeezes your lungs, and you'll cough out whatever's in your lungs, and it'll slowly work its way out all these tiny little branches, and out it will go, and you'll get rid of it. That's how it works for most people. If you have an issue with your lungs, or you're massively overwhelmed with an infection, what can end up happening is pneumonia. So if we look at this lung here, imagine this whole section here is all infected. You can't really get rid of all the infection that's in here. Your body then produces like a pus, a real thick sort of soup, and it's really difficult to then cough this out and get rid of it. What you've also got in your lungs in here is what's known as cilia, which are tiny little hairs. You imagine they sort of do this, and they fan like in your lungs. So whenever you've got something that's caught in your lungs, so you imagine this, it sort of does this, it sort of throws it. It's like little feet kicking a football. And it slowly works it through your lungs till it gets to here, and you have a big cough. And you've had this before, you've coughed up like yellowy green goop. That is the infection that was in your lungs or in your respiratory tract your body's getting rid of. So it's a really important process. But what can happen is if you end up with such a bad infection that your body can't get rid of it, these little hairs, they get covered in mucus. That means then this kind of action where it does this and fans and just gently puts all this infection out of the body, it can't happen. And this is where you end up with something like pneumonia, where a whole side of your lung, even a whole lung if it's a real bad infection, or really bad, you can have both lungs. That's bad. And when that happens, what effectively does is it shuts off here, no carbon dioxide can get out, no air can get in. That's bad. So if we look at a normal functioning lung now, so what the lungs basically do is, around all these alveoli, you've got blood vessels that come along, and what comes in this way is you've got blood that's high in CO2, so you've got large amounts, but it's relatively low in oxygen. Not so much so that it's an issue, because you've still got plenty there to use. So it's high in CO2, low in oxygen, and what ends up happening is, as you breathe, let me get another colour here, what will we do? Let's use green and blue. So the CO2 comes along, and this is a tiny thin layer here. And with this mucus in here that you normally have, CO2 does this, it goes into your lung. When you breathe out, off it goes, and what happens is you have oxygen that comes in, and it passes through and it goes into your blood. And then you circulate this really oxygen-rich blood that goes back through your system. Nice and simple like that. So it gets rid of CO2, which is bad, it gets oxygen, blood becomes really oxygenated, that's good, sends it around your system. That's how lung functions normally. And this process just happens as you breathe, every day, day in, day out. But what happens when you end up with something like COVID-19 or a respiratory illness of some sort? I mentioned before what happens with pneumonia. You get this infection that's in here. What it will do is it will start to clog up a little bit, and you can end up with, if it's a minor infection you might have, so this fluid that's in here might do that. It might cover part of this alveoli. So what will happen is the CO2 can still get out and part of the alveoli, but not a lot. And again, the oxygen coming in, that can still happen. It's just not as efficient. So that's why you can get the shortness of breath. That's why you can feel rubbish. You can feel yourself breathing quite hard. Normally, for most people, that will clear on its own, or with antibiotics, that will help to get rid of that infection. And that's, again, for most people, healthy people, not a massive issue. It just fixes itself and off you go. Life is good. So when we look at a patient that has COVID-19, it works in stages. So if we look at this graph down here, so you imagine sort of two parts to this. For most people, so this is about 75 to 80% of people will stay in this green part. So this is severity of the illness here, this is time. So for most people, they'll stay on this green part, so they'll get this infection, they'll feel a little bit out of breath, they'll maybe cough, they'll maybe have this infection for sort of 7 to 10 days, they feel a little bit poorly, but generally life goes on, it doesn't affect them too much. They'll stay in this phase, so the viral response that they've got, so they've got a massive amount of virus in the body, and you fight it, and it tails off, and this is the severity of it. So most people will get to this point here, it'll keep dipping, and it'll sort of go down like that. They'll all be good, they'll go back to work, none the wiser for it, all good. What happens with people with COVID-19, they get to this point here, but they end up, that this happens for so long, that they end up with this pneumonia. So they end up with part of the lung, or even a whole lung where it's just completely clogged. They cannot breathe, they cannot get rid of this infection. So rather than taking this little dip, they'll start to go up, and they end up in this red part. Red for danger, this is bad. This is where things start going really bad. So most people, it'll be early infection. The first phase, they'll treat it, although they'll fight it and off it'll go. For about 20% of people, they'll end up in this pulmonary phase, and this is bad. Pulmonary basically means your lungs. When they get into this phase, the chances are they're going to have pneumonia, and it's going to be quite bad. And what ends up happening, so there's two parts that happens with this. The lungs, basically, the alveoli fill up with this fluid. You cannot get enough oxygen on. You get no transfer of these gases. And remember, that's the sole purpose of the lungs, it's gas transfer. CO2 goes out, oxygen comes in. This stops happening. So that means the lungs fill up. People then can't breathe. They get really short of breath. And rather than breathing from here, you'll see people breathe from here. It's really shallow breathing. And they'll do this. It's nasty, it's not nice to watch. You can see people are really in distress. When they give people oxygen, what ends up happening is, depending where they are on this infection scale, if they're here, they get a lot of oxygen that comes in. It's really high concentration of oxygen. And rather than little bits going in, there's lots of oxygen goes into the blood. Even though there's lots of oxygen going in, it still doesn't get them to where they are normally without an infection. But what it does is it over-oxygenates, if you like, and it helps them to cope and fight this infection. So that's the first, so this pulmonary phase is split into two parts. Part A is this phase where they can still breathe, they're still doing it on their own. The oxygen levels in their body at this phase of phase 2A, generally speaking, their oxygen levels will be above about 92 to 94% saturation. Remember, if you've been to hospital, you get the little red light they put in your finger. All that basically does is looks at how red your blood is as it's passing around your finger, and it can work out the more red that you have in your blood, the more oxygen you have, the more of your oxygen saturation. So what that does is that works out if it's more than 92%. If you're less than 92%, this is when you are really getting into the danger zone now. You're into phase 2B, and this is when your oxygen level starts dropping. And this is when you're known as hypoxic, which literally means lack of oxygen. Hypoxic is bad. That means that basically you're not getting enough oxygen in, and if you keep going in this route, your body's going to start shutting down, your organs are going to fail, and eventually you're going to die. So that's why people, when they get in this phase, they start coming up here, it gets bad, they put them in oxygen, there's a little dip as they get a little bit better. Some people will recover on their own, just with oxygen. So the British Prime Minister, Boris Johnson, he got to this stage, he was put on oxygen, he wasn't on a ventilator, he recovered when he got to this stage here, on oxygen, which is good. What can end up happening then when you get further, as this fluid level starts getting further and further and further up here, it gets more and more difficult to breathe. And what happens is, you start panicking, your breathing gets quick, everything else starts really getting bad for you. So what the doctors will do is they will then put you on a ventilator. What a ventilator does, rather than your diaphragm here going down and pulling, so it pulls oxygen and air in, what a ventilator does is it pushes it and it forces it in under pressure. What that does then is it forces air. So what they will do, imagine a little guy here. What they basically do is they put a tube that goes down in here. It blocks off your esophagus, which is what goes down into your stomach, blocks that off so that you can't ingest what's in your stomach, completely seals it off, they knock you out, and you connect you up to a machine known as a ventilator. And all that does is basically a pump. And it has a certain volume of air, and that forces it into your lungs. Because you're not having to breathe, you can relax. It takes the strain off you having to breathe. All your muscles around here relax. You need less oxygen because you're not straining quite as much. So it forces, hopefully, all this oxygen into your lungs. And hopefully, once you do that, after a day or two of doing this, things get better, you improve, and you come out the other side. The problem with ventilators is there are downsides to them, and I'll touch on those in a second. What ends up happening when things get further down the line, what happens is something known as ARDS, which is acute respiratory distress syndrome. And what that basically means is there's massive inflammation, and you end up, this tiny little gap here that's so important for gas transfer, it becomes so inflamed and it gets clogged up with liquid because your whole body is basically going into shutdown now. Even if you're on a ventilator and this is pushing oxygen in here, what ends up happening is the oxygen comes down, it basically comes round and it goes straight back out because it cannot pass through all of this. So rather than having the big giant arrow of oxygen going, you're kind of getting tiny dribbles of oxygen. Even though you're on 100% oxygen has been pumped in, your blood oxygen levels start dropping, and they drop quickly. When ARDS kicks in, this is an hour to sort of 2-3 hours from being on oxygen to dying. And it happens that quickly, and it's something that's real dangerous, and it's a nasty illness. When you start getting into this stage, which is phase 3, which is called hyperinflation stage, the inflammatory response phase of your body, it basically is overloaded. It cannot function anymore. The lungs cannot get any oxygen in, and your body literally starts dying. You have not got enough oxygen to sustain life. That's bad. That's when you start getting properly put on a ventilator or an ECMO machine, and I'll touch on that in a second. When ARDS kicks in, it's not good. The chances of surviving it are not high. It's got a pretty poor survival rate, especially when it comes to COVID, and this is what generally kills people, is the ARDS, the acute respiratory distress syndrome. So your severity, again, phase 1, it goes up. Most people, 75-80% of people, drops down, they get better, everything happens nice, 7 to 10 days they're back fighting fit. Some people will end up with an infection that ends up progressing to pneumonia, so this ends up being filled a little bit, they struggle. Some people on their own, even with pneumonia, they can fight the infection, maybe with antibiotics. They'll maybe be in a hospital for a little while, or maybe even at home. Somewhere between 10 to 14 days, they fight the infection, all good. That's phase 2A. If they get into phase 2B, they're hypoxic. They do not have enough oxygen in their body to sustain life. Slowly, they start going downhill. That's when they will be given oxygen, either in a mask or a nasal cannula. Again, some people will survive from this, they will fight the infection, and all they need is that extra oxygen, and they'll get through it and the body will fight it on their own. This is exactly what happened to the British Prime Minister Boris Johnson. Again, they'll fight that, they'll go home, they'll get over it. For some people, and this is the people that they need intensive care, roughly about 5% of people will end up in this inflammatory response phase where they get this hyper inflammation in the body shuts down, all this inflammation, they can't get the gas exchange, they will be put onto a ventilator or an ECMO machine. And the next step for them, if they're unlucky, is death. The body literally just cannot get enough oxygen, shuts down, and you die. There is a little bit of light at the end of the tunnel with this. Even if someone gets ARD, there are things that can be used to treat it. What I want to do is I want to just quickly explain to you ventilators and an ECMO machine and why these are important, and how these are used to treat people with ARDS, because it's so bad. So two options: ventilator, as I said, forces under pressure, it forces air into your lungs, and it basically goes in, inflates your lungs for you. There are downsides to it. If you imagine you have a balloon, I don't know if you remember this as a child, I used to love doing this as a kid. I would get balloons, I would blow them up and then let them go, the way they'd go, blow it up again. After you've done this sort of 7, 8, 9, 10 times, the balloon kind of gets all sort of saggy and wrinkly, and eventually blow it up one time, pop, there's a hole in it, stops working. And this is exactly what happens to people's lungs, and this is one of the downsides of using a ventilator. If you're continually forcing oxygen in here under pressure and it's high concentration of oxygen, there's two things that can damage your lungs quite easily. It's high concentrations of oxygen, because your body's not used to it, and high pressure air. So these two things on a ventilator cause damage to your lungs just by virtue of using them. By virtue of using them, it causes damage, which means your lungs become less efficient, which means you need to force them on the oxygen under even greater pressure, which damages the lungs more, which means you've got to force more oxygen in under more pressure. So remember that balloon I was on about? Imagine what happens to a balloon. It goes all wrinkly and eventually a hole pops in it. This is exactly what can happen with your lungs. They become overused, they become damaged. If you keep doing it, then unfortunately, it can literally pop a hole in your lungs. So this is one of the dangers. One of the risks from using a ventilator is damage. And there's no real way around this, unfortunately, and the longer you're on the ventilator, the more damage that you get. And the longer you're on the ventilator, the more chance that your outcome is going to be poor, the longer you're on it. So death, the longer you're on the ventilator, the more likely it is to happen. Not only that, because you are forcing something through a pipe into your lungs, infection's a big one as well. And if you didn't have pneumonia, which you more than likely would with COVID, it can cause pneumonia, which makes your situation even worse. And I mentioned about the balloon. Eventually it pops a hole. You can have a punctured lung, which is bad. It's not a good thing. Roughly speaking, that is the death rate from COVID if people end up on a ventilator. So it's almost half people that end up on a ventilator won't survive. However, there are rewards that go with this as well. So I've said it's a 47% death rate. That is true. But for 53% of people, roughly half the people that go on a ventilator, this is the only thing that saves their life. Although you might have lung damage and you might have damage for the rest of your life, where you'll maybe lose 20, 30% of your lung capacity, but at least you survived to tell the tale, to then worry about lung issues afterwards. So that's one of the big things. And one thing to remember with any kind of treatment like this, this is a last resort. If you don't do anything, you will die. That's the certainty. With ARDS, you will die. So putting someone on a ventilator, although it sounds counterintuitive and counterproductive, is a good thing. This is why we put people on ventilators. And what it can also do is it can oxygenate the blood. And the reason that's important is not just because up here in your head with the brain, it needs oxygen. It also means things like your liver, your kidneys, all these other organs that you have that need oxygen, they also get oxygen. One of the side effects of lack of oxygen is you can end up with organ failure. So even although you could maybe get through all of this, if you've not got enough oxygen and you're hypoxic for long enough, you'll end up with maybe like your kidneys, your liver, all these other things shutting down and getting real damage from them. The one thing the body will always try and do is send oxygen up to the brain and to the heart, because those are the last things that will always shut down. So those are the rewards that you could potentially have for this. So it's not all bad. Now, an ECMO machine, so this ECMO stands for extracorporeal membrane oxygenation. Very simple terms. All this is a heart and lung machine. What this does, and again, I'll keep this kind of simple. If there are any doctors out there that know way more than I do, then I'm simplifying this massively. There are basically two pipes. One that takes the deoxygenated blood, so we'll do that blue, and then one that takes the oxygenated blood. The blue one, that takes all the blood out of the body, so it literally drains your blood as if you were given blood, puts it into a machine, and what that machine does is it scrubs your blood and takes out the carbon dioxide, puts oxygen into it, comes out the other side of the machine and puts it back in your body. The beauty of that is your heart and your lungs can literally stop, and it will still oxygenate and it will still keep you alive. So that's the good point to that. So that means if someone's lungs are completely filled, you could literally have fluids all the way up to here and all the way down into the lungs. The body will still be oxygenated. The brain will still get oxygen, the liver, kidneys, your gut, your legs, every other part of your body, including your lungs, will all get oxygen to keep them alive, so that your body, all it has to do, one thing only, is fight this infection. So it takes all the strain off your whole entire body and allows your body to fight this. The problem with ECMO machines are they are complicated. They require real specialists to operate them, and not just to operate them, but basically monitor them. And there are risks with everything else. So the risks with an ECMO machine then, one of the big ones, your body is very good at understanding what should be in the body and what shouldn't. So whenever you cut yourself, your blood, it basically clots and you get a scab, which is a normal response for the blood. Your blood knows when it's not inside the body. So what ends up happening with these pipes that take the blood out of your body, your blood goes, hold on a minute, this isn't veins, this isn't arteries, I'm not where I should be, and it goes, whoa, infection, I've got a cut, I've obviously been damaged, let's clot. So what it tries to do is clot in here. So what doctors have to do is give you thrombolytic drugs. So what they basically do is stop the blood from clotting. What that does, it thins your blood, and what that can also mean is you can end up having a stroke for two reasons. One, that the blood is very thin and it can cause you to bleed in places you're not expecting, or if they've not put enough of these thrombolytic drugs in, it can actually mean that you've got clots. So if you ended up with a clot here, it goes through the machine and it comes back in and it ends up somewhere like, let's say it ends up in your heart here. If you imagine your heart, and you've got a series of blood vessels that basically run across your heart and oxygenate it. And one of these gets a clot, it comes along, and let's say it blocks this one here. That means everything basically down from here, so all this does not get oxygen. And if muscle doesn't get oxygen, it turns what you call ischemic, so it dies. Much the same as if you don't get oxygen, you die. If tissue in itself doesn't get oxygen, then the exactly same thing happens. That part of the heart will die, and that's what a heart attack is. Basically, it's lack of oxygen. So you could have a stroke, or these clots can come off and lodge somewhere else and cause other issues. So that's a big one for these machines. And again, another one is infection. Now, the reason being is you've got all this pipework. The blood has been taken out of the body, it's getting put through all this, and it's then getting forced back into the body. So it's not getting filtered through the kidneys, it's not getting filtered through the lungs or anything. It's pure infection, can go straight in, and that's bad, obviously. Probably one of the biggest points with an ECMO machine, there are very few of these machines around. They're expensive. They require very, very advanced care. They need specialists to operate them. So very specialised, so there's very few of them. And the risk of using these, again, if we look at this specifically to ARDS, using one of these, it's got about 45% mortality rate. So again, it's about half. It's not great odds if you end up in one of these. So there's the downsides. The rewards, again, 45% fatality rate. It does mean there's a 55% chance you're going to live off the back of this, which is good. So, plus points. Lungs are bypassed. That allows them to relax, calm down, fight an infection, all this to disappear, which it will eventually, once the body gets a hold of it. So it then allows the body to recover. So not just the lungs, but the body can recover as well. So it will recover. And the important thing with this one is it doesn't damage lungs. No. Trying to spell. Because it isn't pumping anything into lungs, it doesn't damage them, which is good. And that means when you're in this phase, this doesn't become so much of an issue because the body's not trying to fight the lungs. So all this aside, if we look at just COVID in and of itself, there are certain things that make you more predisposed to having a bad reaction to COVID. And there's certain illnesses, and I use this is what I used to use when I was an EMT, was death. So whenever we used to speak to people, I would never tell them it was death, but I would always ask them the same questions every time. Do you have diabetes, epilepsy, asthma, or breathing issues? You ever suffer from a TIA, which is a transient ischemic attack? That's a stroke. So I'd always, you ever suffer from a stroke or any heart conditions? And then H was high blood pressure. So if you have diabetes, epilepsy, asthma, or breathing issues, so things like COPD, all those kind of things, that was what I would class as breathing issues. If you've had stroke or heart attack or heart issues, or high blood pressure, you are not in the best placed position should you end up with COVID-19. And one is probably the biggest marker that we find in the United States for people: obesity. That is the single biggest factor that seems to be driving this. Most people that are obese generally tend to have one of these other issues, so that's why it kind of comes in. And I think it's something like 40% of the United States population are obese. 40%, which is huge. So if you have any of those conditions or you're obese, then the chances are you're not going to have a great reaction to COVID. Now, I mentioned about posture and why this is so important. One of the things that they've found with people who are on ventilators or they're on an ECMO machine, with a ventilator, not an ECMO. If people are on a ventilator and lying on the back, remember I said about posture with breathing. If you're lying on your back, it's very difficult, so it can cause extra strain on the lungs. So what they've found is with a lot of patients, what they end up tending to do is they'll either elevate them slightly, or what they'll do is they'll actually put them on the front and they'll elevate them so the head's down slightly. And this helps for quite a few reasons. With the ventilator, it means they can actually drain all the fluid and everything that's in the lungs. They can get that out. And when they're on the front, don't know the full ins and outs why, but the rates of survival went up. I think it was about 20%. It was either 16 or 20%. I can't remember which one it was. And it helped people. So if you do end up with someone that has this illness and they end up putting them on the stomach or even having them sort of bent over, you know why. It's for posture and it's to allow all this fluid and stuff to drain. Just quickly have a look around, make sure that I have not forgotten anything within that. No. So hopefully that gives you a real good insight as to COVID-19 and why it's so prevalent, why it's a big issue for people when they don't self-isolate, based on what I've said about how infections spread. And if you do get COVID-19, for the majority of people, and we're talking about 75 to 80% of people are going to be okay. And when I say okay, I don't mean you're going to feel absolutely fine. It'll be like having pretty bad flu for 75% to 80% of people. 20% of people will need hospitalisation. 15% will end up in this pulmonary phase, probably end up on oxygen of some sort. And 5%, unfortunately, will end up down in this area here, which is the inflammatory response phase, where the outcomes are not great. So hopefully that has really given you an insight. If you have any questions, any thoughts, anything you want to know about it, then please get in touch, let me know. And if there are any doctors that are out there and you want to add anything to this, or you'd like to see me add to it, then please let me know, because I want to make sure that people are getting facts and they're not just getting people's opinion on things. I want to give people the most up-to-date information that we've got. Just for your information, this was recorded, I think today is the 13th of April, it's 13th to 14th of April. So this is the most up-to-date information that we've got as of now. There might be things that will change in the meantime.